Today's problem is minimum k consecutive bit flips. You are difficulty is hard. Accuracy is quite high for a hard problem. You are given a binary array containing only zeros and ones and an integer k. In one operation, you can select a contiguous subarray of length k and flip all of its bits. Change every 0 to a 1, change every 1 to a 0. Your task is to find the minimum number of such operations required to make the entire array consist of only ones. If it's not possible, return -1. All right. Before we look at the examples, let's go down here. Okay, array size between 1 and 10 to the 6th, 1 million. K between 1 and the array size. Time complexity, O of n. Auxiliary space, O of k. Gotta think about that. Do we really need, well, okay. Company tags. Okay, so looking at the companies here that ask this question. This is a hard question, but it's not like nobody would ask you this question, but if you're not interviewing at, one of the most technically demanding companies in the world, you probably would not be asked this question. What else? Prefix sum, bit magic, sliding window, Q. Prefix sum. Well, I mean, some of these we're not going to use, but I mean, apparently there's multiple ways to solve this. I saw the prefix sum. I was trying to think about how to do it with a prefix sum. I couldn't think of anything. Sliding window we're going to use. We're not going to do anything magic. We're not going to use a Q. And it doesn't say greedy. I mean, I would call the approach that we're going to use here a greedy algorithm, but okay. Let's get the examples. So it looks like what they're going to do is they're going to flip these first two zeros. And so then we would have 4 ones at the beginning, right? 2, 3. The next thing they're going to flip is they're going to flip this 0 and this 1. So then we're going to have 5 ones. This is going to be a 0. The next thing they're going to do is flip these two. This 1 is now going to be a 0. So they're going to flip that. The 0 will go back to a 1. This 1 will go to a 0. Then we'll have all zeros, I'm sorry, all ones except for 2 zeros in this position. And we can flip them. So that's four flips. Okay. All right, let's take a look at the algorithm here. Let's scoot this over. You see everything now? All right. Can I move this a little bit more? I can't, as far as it goes. Okay. All right. I think I'm going to be able to get everything in the window here. So what we get in, the input is the array. We're going to do this example here, the first example, and k, the length of the what did they call it? The length of the subarray that we are allowed to flip. Okay. N, array length. I need to scoot that up. I need to be able to see this. All right. The only thing that we can't see here is that at the end we're going to return flip count, but we can remember that. All right, flip count. Flip count keeps track of the number of flips that we do. And that's what the method is going to return, current flips. Okay, current flips. Current flips refers to current flips within the current sliding window, within the current window of length K. What does that mean? Well, for example, let's look at the first example here, index 2 and 3. All right, if we said, when we get to index 2, if we said, all right, we're going to do a flip here. Well, it's going to flip to index 2. It's also going to flip index 3. Now, when we get to index 3, we're still going to be looking at a 0, but the current flips within the window is going to be 1. We're going to use that information to say, okay, well, effectively this number is a 1. Okay, we don't like look ahead and flip numbers ahead of the number that we're currently processing. So, current flips, that is, when we get to a number, its actual value is maybe not what we're looking at because we have done a flip within the window. I don't know, maybe I over-explained that, but yeah, current flips is the number of flips that we've done within the current window of length K, and we have an integer array called isFlipped, and we use that to keep track of whether or not the digit at a certain index has been flipped. So actually our auxiliary space is not going to be O of K, it's going to be O of N. I hadn't seen that O of K, but you know, if you really had to get it to O of K, you could do it, because anything outside the current window, we don't care if it's flipped or it isn't. So the easiest way to do it is just to have an array of length n and keep track of whether or not a digit has been flipped. But you could have kind of a sliding isFlipped window of length k. Okay. Okay, we're going to process it one at a time. One at a time. I need a pen here. All right. Wait a second. Okay, so this has got to get off of there. Okay, we'll go here. We'll go here. All right. I is 1 to n. All right. I guess I should probably keep track of it here. Oh, that's going to write in white? That's not what I want. Hold on. This needs to write in black. Okay. Should probably keep track of what I is. I is going to start out at 0. Is I greater than or equal to k? Now, what we're checking there is that if I is greater than or equal to k, then we don't care about digits that were flipped outside, prior to the current sliding window. We're not there yet. I is not greater than or equal to k. All right. Effectively 0. So that means either the digit that we're looking at is 0, or the digit that we're looking at is 1, and we've done an odd number of flips within the current window. So let's take a look at that. Effectively 0. In this case, does the array equal 0? No. Does it equal 1? Yes, but we don't have any current flips. So effectively 0 here is false. Okay. This, go back up. This is now 1. Is 1 greater than or equal to 2? No. Is that is that effectively 0? I'm going to put this here. Just to kind of keep, you know what, I'm just going to keep track of where we are like this. I'm going to put the is flipped array. Yeah, actually, let me put it, I'll build it up here. All right, so those are zeros. Is that effectively 0? No. All right. Go up again. I is now 2. And we're here. All right. So when I say we're going to do a greedy approach, if we see a 0, we're going to flip it. The reason being that if we say, well, it's a 0, but we're not going to flip it, I mean, eventually we're going to have to flip it because all the digits need to be 1. It's easier to flip it now than to bypass it and then try to come back later and figure out a way to flip it. So we see a 0, we're going to flip it. All right, I is greater than or equal to k. 2, yes, now it is. All right. Current flips is flipped at 2 minus 2, 0. Okay, it's 0. Current flips is 0. All right. Effectively 0. That is a 0. So yeah, it's effectively 0. All right. If I plus k is greater than n, yeah, what that means is that we are about to we're going out of the bounds of the array. In which case we're going to have to return -1. All right, so let's do this. We're going to do a flip. Flip count is incremented. All right, so flip count is now 1. Current flips is incremented. So we have 1 flip in the current window. Is flipped at I equals 1. Okay, we'll go back up. Now we are on index 3. All right, is this effectively 0? Actually, it's not. It looks like a 0, but the number of current flips is 1. So it does equal 0, but current flips mod 2 does not equal 0. What that means is that by doing the flip at index 2, we effectively flipped index 3. So that is a 1 for our purposes. Okay, if effectively 0, no, nothing down here. All right, and that is not going to be flipped. All right, next we go to 4. That is here. Is this effectively 0? Well, yeah. Oh, wait a minute. We're not going to do effectively 0 yet. 4. Yeah. Okay. So that's good. So current flips, we're going to subtract is flipped at 4 minus 2. That is right here. This flip is now out of the window. Okay. So current flips goes back to 0. Okay. So is index 5 effectively 0? Yes, because there's no flips in the current window. All right, if it is effectively 0, have we gone beyond the bounds of the array? No. Flip count is going to be incremented. 2. Okay, so we'll do a flip count. Current flips is incremented. 1. Is flipped at I equals 1. All right, so we're flipping index, what, 4 and 5 there? Yes. All right. Back up, we are on index 5, which is here. Okay. Yes, current flips is flipped 5 minus 2. Index 3 is 0, so that doesn't affect the current flips. Is this number effectively 0? It is, because it equals 1, and the current flips mod 2 does not equal 0. So when we flip, when we did the flip at index 4, it flips two numbers. It flips 4, it also flips 5. So 5 is effectively 0. So that means flip count is incremented. It's 3. Current flips is incremented. It's 2. Is flipped is 1. Right here. Okay. Back up to the next number. We are on index 6. Current flips, 6 minus 2 is 4. Where's index 4? 0, 1, 2, 3, 4. Okay, yeah, so that would subtract 1. So current flips would go from 2 back to 1, because this index 4 has moved out of the current window. Okay. Is this number effectively 0? Well, it's a 1, and the current flips are odd. So yes, that is effectively 0. It's 1 with an odd number of flips. Okay, so we'll go effectively 0. We're not past the end of the array. Flip count is going to go to 4. Current flips, incremented. It's 2. Is flipped, right here, is 1. We'll go to the next digit, 7. So we are here. Is that number effectively 0? Oh, wait, sorry. Current flips is flipped. 7 minus 2 is 5. 0, 1, 2, 3, 4, 5. All right, so we have to subtract 1 from current flips. Current flips is 1. So the number that we are looking at, is that number effectively 0? It's not. It is not effectively 0 because it is, well, it is 0, but we have a current flip within the window. So it's really a 1. So we're not going to do anything there. That is not going to get flipped. All right. Next number, 8. We're here. Okay. We'll go down here. Is flipped. 8 minus 2 is 6. 0, 1, 2, 3, 4, 5, 6. All right, so we subtract 1 from current flips. Current flips is 0. There are no current flips within the current window, which is this this right here. There are no current flips there. The last current flip was at index 0, 1, 2, 3, 6. We are now on index 8. All right, is that effectively 0? It's a 1 and there are no current flips. So no, it is not effectively 0. So we don't do anything. We go to 9. And actually, we're just going to repeat this process through the rest of the array. Those 1s are 1s. You know, we haven't done any flips recently enough for those to be effectively 0. So we're going to get to the end of this, and our flip count is going to be 4, which as it happens is the correct answer. All right, so let's kind of review this. Current flips. We're taking a greedy approach to this. Anytime we see a 0, we flip it. And we flip, we flip a group of k numbers. Now we have to keep track of current flips in the window, because starting from where we flip it, there's going to be k numbers that get flipped. So when we go to these next numbers, they are not going to be what they look like. Or potentially they are not going to be what they look like. So we keep track of it to see, what is the effective value given the flips that we've already done. And what else? Okay, so if any bit that is effectively 0, again, because we are taking a greedy approach and we are flipping all of the zeros, then we will increment the flip count, increment current flips, keep track of where we did the flips, and that should give us the correct answer. I think I wanted to say one more thing about this because we didn't use it. If the current bit is effectively 0, we need to perform a flip. Yes, we can't perform a k-bit flip if it goes out of bounds. What does that mean? Well, if you worked through this second example, what you would find is that you would get to this last 0 here, and you would want to flip it. Now the index of that, I, is 6. K in this example is 3. So 6 plus 3 is 9. The length of the array, n, is 7. So 9 is greater than 7. You can't flip that because you can only flip, in this example, in groups of 3. And there is nothing after this element to be flipped. So you're stuck. You are stuck. And you have to return a failure code. All right. Let's see. Exit drawing. Okay, yeah, let's do that. Let me move this back over here. All right. We'll try to run it. All right, good. You should like that video because it was hard. You can subscribe to the channel and you get notified about problems of the day as they occur, which should be once every weekday. Hard, medium, easy. Yeah, that's it, and we'll see you next time.